As the name suggests, in these problems, we have a number of variables and a bunch of constraints on these variables. And the goal is to come up with an assignment that satisfies most number of constraints at the same time. Let's stay concrete and work through an example. The example that I chose is the magic square puzzle. I'm sure everyone in this room have seen one form or another a magic square puzzle. Here I'm going to tell you about my favorite one. We have a 3x3 square. And the goal is to arrange the numbers +1, -1 in the cells of this square, such that a number of constraints are satisfied. The constraints are that we want the product of every row and column to be +1, except for the last column where we want the product to be -1. Okay, so this is a constraint satisfaction problem with 9 variables and 6 constraints. And the question is, can we satisfy all of them at the same time? A moment's thought shows that, no, this is impossible. And the reason for it is that if I could come up with an assignment that satisfies all the constraints, then a row first product of all the variables would yield +1, whereas a column first product of the variables would yield a -1, and this is a contradiction. So this is a very good representative of classical constraint satisfaction problems. In quantum computer science, we study exactly the same problems, constraint satisfaction problems, exactly this one, for example. But the difference is that the domain of the variables, instead of being a discrete binary, like here +/-1, the domain of the variables in the quantum version of these problems would be higher dimensional generalizations of plus and -1. It turns out that the higher dimensional generalization of +/-1 are unitary matrices. +/-1 themselves are special unitary matrices. And it turns out, so the quantum magic square would be trying to assign matrices, unitary matrices, to the cells, such that the product of the rows and columns are ± identity operators. Okay, it turns out in this more general domain, there is a solution that satisfies all the constraints at the same time. The specifics of this assignment doesn't matter. It's these X, Y, Z are famous matrices that show up all over quantum mechanics, and their tensor product would produce the assignment that satisfies all the constraints. Again, doesn't matter what they are, but just this mere fact that classically magic square doesn't have a solution, but quantumly it does, really lies at the heart of a lot of applications of quantum computer science, in cryptography, in complexity theory. But the applications go far beyond computer science. In fact, magic square was proposed by physicists a long time before computer scientists had started thinking about these problems. And the goal they had in mind was to design an experiment that shows that nature behaves according to the laws of quantum mechanics rather than classical mechanics. In fact, this was the experimental validation at the core of which was a puzzle like magic square, was the subject of the Nobel Prize in physics last year. So now that we can tell that these problems are important all over the place, let me tell you about some of the things that we know about them. Unlike the example of magic square, which was very easy to reason about, in general, quantum CSPs are really, really hard, much harder than classical CSPs. But there are very famous examples like magic square. There are many others where finding a quantum solution is actually easier sometimes than the classical solution. And we were intrigued by this problem. We wanted to understand what are exactly these classes of problems. In a preprint that is currently under review with my co-authors, we were able to show that there is a class of constraint satisfaction problems, technically known as Max-to-Lin problems, where this phenomenon occurs, where the quantum solution can be found more efficiently, whereas classically we don't know whether we could do that or not. Just one last thing, there are a lot of open problems in this kind of like line of thinking. One is the following. every classical solution is a quantum solution. I told you plus minus one in the magic square are unitary operators, right? So given this kind of observation, one could ask, if I am given a quantum solution, could I extract a good classical solution from it? I told you in the previous slide, there are some problems where we can actually solve the quantum problem easier. So could I extract a good classical solution from a quantum solution? And we have some preliminary result on this one that tells us that there is a general algorithm that can take any quantum solution and extract a good classical solution. And it works on all those problems that I mentioned in the last slide, the max-to-lean problems. Okay, and so far it only reproduces the best known classical algorithms, but this is very preliminary, and we hope that we could go beyond what classical literature can provide us. All right, that's all I have.
Thanks a lot, Hamoon. Maybe we can defer questions to the break. Thank you. So next we have